On learning target 29, we're dealing with ideal springs and the forces and potential energy associated with those. Now, an ideal spring is different from a real-world spring in that we can't stretch it out too far. You know how in a real spring, if you stretch it out, it won't go back to its original shape. So ideal springs, they always want to go back to their original shape. And the farther we stretch them, the harder they pull to get back to their original shape. And so this can be expressed in an equation that we call Hooke's law, which is usually written as F equals negative kx, and we give that the little subscript S for spring. Spring force is equal to negative kx, where k is the spring constant. And like I said, as we get farther away from the original length or the original position of that spring, the force is going to go up at a linear rate. So k is that rate of force increase as a function of distance. And then x is just going to be the distance stretched from the resting position or from the relaxed length of the spring. And then the negative sign there just indicates that whichever direction we pull on that object, the spring is trying to pull it back into its original position. So if I pull it to the right, the spring will be pulling to the left. If we push to the left, the spring will be pushing back to the right, always back to the original position. And then the potential energy, not x, but potential energy for a spring, is going to take the form of 1/2 kx squared. And again, as with all potential energies, that's going to be measured in joules. Now this one, it doesn't matter whether we're stretching or compressing. There's no direction or no sign change with the potential energy. We can have a minimum value of 0 for potential energy, and that's going to be when the x value, the stretch distance, is 0. But if we stretch or if we compress the spring, since that x gets squared, even if I used a positive or a negative sign for x, we lose that information. So minimum value can have a 0. We can't have negative potential energy for springs, or elastic potential energy is the name of that. So let's look at a couple of examples here. The spring shown has a spring constant of 250 newtons per meter. That means if we apply 250 newtons of force, we could stretch it or compress it by 1 meter. If we applied 500 newtons of force, we could stretch or compress by 2 meters, and so on. And then from the relaxed position up here to the stretched out position, you can see that this mass m has moved a distance of 0.50 meters. So we'll find out what the force from that spring and what the potential energy from that spring would be in this case. So force from the spring is going to be equal to negative kx, and k was 250 newtons per meter. X was 0.50 meters. So the force from the spring is equal to negative 125 newtons, or 125 newtons to the left. So we stretched it out to the right, force pulls it back to the left, trying to get it back to its original shape. For the potential energy, we do 1/2 kx squared, that's US, it's 1/2 kx squared, so that's 1/2 times 250 newtons times 0.50 meters squared. And again, it doesn't matter whether we have that 0.50 as a positive or a negative, because it gets squared. We lose that information anyway. So US then is going to be 1/2 times 250 newtons, newtons per meter rather, times 0.25 square meters. So S is going to be, let's see, 125 divided by 4. That must be, let's see, 31, let's see, 125, 62.5, 31.75. And the units on that are joules, or we have one factor of meters cancel out, so it's newtons times meters. Usually for energy, though, we just use joules.